Hello, this is Mike Antosh with the Engineering Technology Podcast from Prolytics. I have with me today David Wicker. And, David, we're getting started at Prolytics with this podcast idea. We've tried to come up with content, but today we're going to fall back on something that we've been working on for 7 years and should be easy, free-flowing. So, no. We're gonna just trust our brains here to walk us through it. We're gonna talk about automated SIS testing. So before I go any further, I gotta say, what is SIS? Let's go ahead and define that real quick.
SIS is a safety instrumented system, right? So we work in Petrochem. So these facilities, refineries, chemical plants, they've got control systems that actually run the process and try to keep it within a certain range for operation. And then the safety system that's there waiting if it gets out of bounds to essentially shut everything down. So that's what we're talking about today.
Okay, so safety instrumented systems really in all facets of manufacturing, industrial manufacturing, right? They're used all over the place. And your background, how long have you been working with SIS systems?
19 years now.
19 years, okay. And that started, what was the very first PLC you worked with?
Control Logics PLC.
Allen Bradley,
Allen
correct?
Bradley Control
yes.
Logics, yeah.
And the best one that you've worked with? No, you don't have to answer that.
Triconics.
We don't want to.
I
Triconics.
like Triconics.
Okay.
Yeah.
I don't want to offend any of our potential sponsors. Now, safety instrument system. So what you said was, if you have some type of industrial process, it generally has like a control system that's supposed to run it, right? And then it has, if that isn't working, it has a safety system to be the bounds. And one of our common mentors, a common denominator amongst our careers was Victor Mozicek. And I think he described it as the road, right? So the control system is the road. You're driving down the road in your vehicle like normal. The safety system is like the fence.
Right.
So something falls asleep, boom, you hit the fence. You get distracted, you hit the fence, it brings you back. It shuts you, and usually shuts you down, right?
Shuts you down,
so the control system will allow you to sort of flex and then try to bring you back, like slow a pump down or close a valve or do something, and it's sort of always working like your cruise control, right? Going up a hill, going down, adjusting, or even in today's world, your cruise control that even slows down for cars in front of you and all that. What do they call that?
Adaptive cruise control.
Adaptive cruise control. But the safety system is more like it just, boom, that bad idea, you're shut down and shuts you down. So we're talking about safety systems. Now, in the industry, those guys are under more scrutiny than the control system. Is that right?
Yeah.
And they have to be tested. Is that correct?
Yeah.
More frequently, and to make sure that they meet the requirements that they were designed to, right?
By more frequently, you mean they have to be tested at all. Yeah.
Well, the control system is almost tested on a daily basis because it's theoretically the thing that's just doing the normal business,
But
right?
it's being modified also on a daily basis, and that's part of the requirements around the safety system is that you have to do management of change. You can't just run in there and change something willy-nilly and download it to processor and be running with something new.
I sense a little bit of so there's the process control experts and there's the safety experts. I see a little bit of a dynamic here between these two.
They get to do stuff all day long every day. We sit and wait for 6 years, and then a trip needs to happen, and it's our time to shine. And we want to make sure that system does what it's supposed to do.
So that safety system is just sitting there waiting, and it knows things like, ooh, if this pressure gets too high, I have to shut down. If this temperature gets too high, or this flow gets too low, that means that there's a risk to the environment. There's a risk to a human. There's something at risk there, right?
Yeah, and we probably oversimplify. We for sure oversimplify. They can get incredibly complex, and many safety instrumented systems, they perform functions on a daily basis, but the typical system is lying there and wait, and it's monitoring, and it's ready to respond. Very quickly.
My experience started out in upstream offshore Gulf of Mexico, there the safety system is waiting and waiting for something to happen that's abnormal and then shutting it down. Everybody regroups, figures out what was the problem, and then restart the facility. I think though I've listened to you talk about like burner management systems and boilers, and there is a little bit more sophistication to the way those work. Is that right?
Right. There's sequence-based systems. Really, fired equipment is very complex, especially during startup and shutdown. The sequencing of the final elements that has to occur, the light-off sequence. And if you get that wrong, it's very explosive, very dangerous. So those times of transition, both during startup and shutdown, are especially dangerous. But then really can be a lot of hidden failures in the safety system. One, in the instrumentation itself, is it still functioning properly? That's maybe a little outside of the scope of what we're going to talk about today. Two, there's the configuration as well, which could be, you assume everything's going to work right when it needs to, but if it doesn't get exercised, if there's no demand on the system, in some cases you may never find out if it actually does in real life what it's designed to do. But if those conditions actually exist, then you need to know that the system's going to take action and do it appropriately.
Yeah, I mean, to use a practical example, to me, there's, your airbag is a similar situation. It's a safety system in your vehicle. You can't test it. I mean, in that instance, you can't really test it, right?
Right. Yeah. You don't want to.
It's got to work, and it might sit there for years just waiting to do its job, and it's got to be ready, and the safety system has to be ready. So when did these systems get tested?
Traditionally, or how is this being done in industry now?
At what point in their life cycle? Like someone has to you got to create a project where someone has to say, we need a safety system. It's supposed to do these things. So someone then has to program that, right? And then you have to commission it, and then you have to run it forever as long as the facility runs. So at what point along that life cycle does it get tested?
Well, for sure when you install and commission the system, right? So we come from an engineering project background. We were designing these systems, building them, configuring them, commissioning them, testing them as part of that, which is a big focus of what we're talking about today. So definitely on a project, and then you produce a lot of documentation that goes along with that system and how it's supposed to function. You program it according to those documents, you test it according to those documents, then you put it into place, you test it at site. So we go through things traditionally called like an FAT, or factory acceptance test. That's in whoever programmed the system, built the system. You'll test it there once. You'll move it to site. You'll do a site acceptance test, an SAT as it's commonly referred to. Then you'll actually do commissioning, and you'll do a functional acceptance test. And then that test, or a subset of that, gets repeated at some frequency. And there's a lot of math driving this. Functional safety is a whole discipline driving the calculations for how safe the system is, how safe it needs to be, and then along with that, how often do you need to test it to ensure that it can still reliably perform its function.
Okay, so I'm going to relate this at a high level. If you think about a project team, where to build a project team, you've got to have structural engineers and process engineers and instrument engineers and electrical engineers. They all come together to design a facility. At some point, that gets handed over to and they are supposed to know how it's supposed to run. That gets handed over to an automation engineering team. At that point, that's when this programming happens, right? So someone goes into one of those systems you mentioned earlier, Allen Bradley or Triconix or Yokogawa or Honeywell or HEMA, and they program the logic to meet what the engineering team has said is supposed to happen, right? And that's where the first test happens, is a factory acceptance test to say that automation team built it to the spec that was provided, right?
That's right.
And then you pick that thing up and you travel to wherever this facility is, you set it in place, and you test it again, a site acceptance, to make sure that everything that you unplugged and did at the office is now still working. And then on shutdown intervals, so like once a year or once every couple of years.
You're talking like 5 to 6 year. For a lot of these facilities, they're pushing that out as long as they can, because they're making money when they're up and running. So they've optimized their workflows to run for as long periods of time as possible between outages.
Okay. Now what we're talking about is specifically software to do an automated test.
Mm-hmm.
Why is that even needed?
Well, again, coming from an engineering project background, it takes a lot of time and effort to put a test procedure together. Not only putting that test procedure document, but then executing that. Depending on the actual platform you're using, the mechanism for driving a simulation, you're not connected. Many times, the first time you test this, you're not connected to the field. You don't even necessarily want to send dozens of people out into the field to drive signals from the actual transmitters and monitor things at the final elements. That can come later. You're trying to test as many scenarios as possible on your system, and do this in a quick way through like simulation or through some sort of techniques. So really, that's how we got into this. Is like we were designing, building these systems, programming them, commissioning them, and testing them. But a lot of times you fall down on the testing side if you don't have a good plan. You don't take the time to develop a test procedure. And you don't have any tools or technology to make the implementation, the execution of that procedure faster.
So you, as the automation engineer, were testing your own work.
Yeah. So
Okay.
not ideal, right? Really, not even intentional bias, so unintentional bias. You're going to read the design document. Say you've got a narrative, cause and effect matrix.
So let me stop you right there. So when you say a narrative, you really mean like a Word document that says, hey, we're running this boiler, and it's supposed to start up this way, and it's supposed to shut down this way. And it might also have a cause and effect, which is more of a matrix where you've got inputs on one side, and you've got their resulting outputs. So if this thing happens, then this effect happens. So those are what you would call some of your design documents. Those are the inputs that go to the program, right?
And you've got safety. There's others. There's safety requirement specs as really one of the main documents, but in our experience, a lot of times you'll find references in those that point to a cause and effect or logic diagrams or some other narrative document.
So that's everything that the programmer takes into account. And then you can also have a test procedure, which is a step-by-step guide as to how to test that. Right. How do those get created often in the industry?
Traditionally, it's manual process, either a Microsoft Word or Excel document that an engineer's taken the design documents and then written out a step-by-step test to validate that the configuration actually matches that design.
Okay, so then when you sit down to test this thing, you got the programmer, they have all the documents that they were given, the programmer, then you have this procedure, and how does that test go? Like in the older methodology, what's the experience like?
Very old school, right? If you're in a factory, you're at an office, you're not connected with anything. Folks trying to do this a little faster would physically hardwire devices, potentiometers, switches, lamps, into your system in order to exercise we call the I/O, the inputs and the outputs, the hardwired inputs and outputs of a system. They would exercise those physically through the actual hardware of the system. Folks have moved away from that. It's very labor intensive, very difficult. And IC 61511, for example, allows you to do testing in parts. And most folks now are moving towards a more segmented testing methodology where they're pulling off the logic, the configuration, and they're doing all the testing on that separate from the actual hardware and the physical system. And
for the primary purpose of this message, we're going to talk about that logic, right?
Really.
So all of the sophisticated programming that's supposed to make this thing work. And then the test, it can be a bit of a slow experience, clicking through one step at a time, validating it, looking at it, highlighting it, saying, okay, yes, that happened. It's a witness type situation. Reset everything, restart. Is that the kind of experience you're talking about?
Yes, and it's painfully slow without any tools. Most likely you're interacting directly with the vendor software for whatever platform you're using. And you're sending things like disable and force commands on a tag by tag basis. So one I/O at a time, really on the input side. You're overriding those values, you're typing in new values, and you're confirming. If you're doing that manually, it might take you 5-10 seconds per tag. and you're talking about systems that have hundreds, if not thousands, of tags. It's very slow even to get a system set up. And then if you're dealing with a complex piece of equipment, say like a boiler, furnace, fired equipment, you'll have to walk it through a startup sequence, which involves a purge, several permissives you need to check, and then ultimately a light-off sequence where things have to transition very quickly within like 10 seconds, for example. Very, very difficult to manually manipulate that many values to get a system up and running, to actually even test a safety system without any kind of simulation capability.
Okay. And what I always like to refer back to, like, junior high level math, if possible. That's the most fun level of math for me. And the word permutation comes to mind because you're talking about all of these permutations of things that are supposed to happen, right? This input and this one and this scenario. So it's just thousands of scenarios that you're essentially testing, right? Because you're supposed to exercise all of the different weird things that could happen to make sure that when this thing is called into action in the facility, it actually protects what it's supposed to protect, right?
And to put that into context, that, typically we see, 800, 1,000 pages of test procedure that you need to run on a system. If you're sitting there manually having to walk through each of those steps, not only follow along with the procedure, but manipulate all of the signals manually, it's very difficult to logistically even do, much less keep your focus, be monitoring the system to make sure it's actually doing what it's supposed to. That's what we found is so many folks were so concerned with the logistics of running a test that they just completely lose focus on what they're supposed to even be monitoring, and things would slip all the way through a project where you thought you had a good test, but you missed something that you really should have caught.
So it sounds boring.
It can be
or
boring.
Monotonous is maybe a more sophisticated word to use, but
the traditional way of doing this is very boring, time intensive, and expensive. That's the problem.
So we wanted to focus on four. Now, so there's an upfront test, the factory acceptance test, and then there's the long-term usage down the line. The software that we have is applicable in both cases, and really we've seen value in that already commissioned plant that's going through turnaround, and we can test this system more thoroughly and at the right time, and that's all about timing. But if you look at the big picture, we had, I think, 4 items I wanted to hear from you on related to the benefits. I think we're going to talk about cost. We're going to talk about documentation, repeatability, and quality. So let's work up to cost, because that's the one everyone's going to lean on first. But tell me about the quality difference in this if you're going to automate this test. So you're really talking about, we're going to take all of the requirements of this system, and we are going to build a procedure that will automatically run through and do this full test. We can witness it, right? But that's ultimately what the solution to this is. Is that correct?
That's right. And we're going to hit on a lot of things here, but ultimately, the best test that you get traditionally on these systems is the first test, right? The factor acceptance test. You're doing the most thorough, most robust test. And at that point, you're not having a lot of changes that aren't part of the project. You install and you commission something. From that point on, it's got a life cycle. And yes, there are requirements to do that proof testing at some interval on the system. But what we find is folks need to make changes to the system. And sometimes they test it effectively and sometimes they don't. But the integrity of the system as a whole can degrade over time. And what we've seen with the traditional testing approach is you don't typically get as thorough of a test on those follow-up proof tests while a system's in operation as you do that first time. So, for example, you have 2 out of 3 analog inputs, like transmitters that are voted together. While you're doing a FAT, you'll walk through multiple combinations of those devices to prove that they do what they're supposed to do, that voting integrity is in place, your degradation is in place, and all that. Well, fast forward to the proof test, now you're down for turnaround. You do all this work, and they give you a shift or two to test a system out to make sure it's safe before they start it back up. And everyone's breathing down your neck, and you have to test it as fast as possible. Just the logistics of that situation, what that results in industry is as minimal of a proof test as possible to prove the basic function. So you're sending techs out to the field with a traditional test. They're physically hooking up to devices, and they're combining both like a loop check and many times calibrations, loop check, and a logic test all in one package. That takes a long time. So they'll test maybe one combination and prove the basic safety is in place, the basic integrity of their safety instrumented functions are in place, and then they're going to move on. Okay.
So from a quality standpoint, what you're really saying is that the crucial nature of the activity drives rush, essentially. And so if you have this thorough test from the beginning that you did the very first time, and it meets all of the requirements of the documents, then you can reapply that test and have confidence. So we can run these tests in a manual mode where you go one step at a time, mm-hmm. or we can run it in a semi-automated mode where you break it up into functional pieces of the plant, or you can set it to run throughout the entirety of the program and test every single permutation that it's supposed to test. Then you get a report out that says pass, fail. Is that right?
Absolutely. So that's what we help folks move towards is a segmented testing methodology. And that's one thing simulation, like our software test drive, enables is a fully auditable and automated test that you can run anytime. So you can decouple that from your turnaround frequency, your actual outage time, and take the time outside of that critical path, that really stressful period of time. You can do all of these extensive tests outside of that, and then just test the real specific physical things you need to test during that period.
Okay,
in a much shorter time.
So we're talking about a software package, but we're also talking about a philosophy of segmented testing, which we could dive into more there. But basically, the sophisticated logic can be tested in a window that's not as critical. But we started talking quality and saying, okay, we're building this full test, which is something that's better than when you're doing it one at a time as a human, and then more thorough. Yeah. And then our next point was repeatability, mm-hmm. and essentially it is repeatable because the entire test is built and locked into the procedure. So you can rerun that and have confidence that you're running the same test.
Exactly.
Now, I myself have done this testing, and I had a highlighter, and I had initials, and someone sitting with me, and we said, okay, we did that. Everyone saw it work, highlight it, put my initials on it, go to lunch, pick right back up, do the same thing all day long. Yeah. I can't really repeat that test.
You can't, and you might get a fantastic test out of that. I've done that myself on projects where there wasn't budget allocated to developing the procedures, but you can still run a good test. A couple problems, though. One is the repeatability, because it's not fully documented on exactly how to run that test. And the second is auditability. You run that test and you've got a highlighted document, but really you don't have any proof of what you did and what the system response was. And you're relying on humans physically witnessing with their eyes and watching everything that's happening.
So how is Prolytic's test drive solution different on the documentation side of it?
So we wanted to build a system where you didn't have to separately maintain your test procedure document and also some sort of simulation software. So we combine the two of those. In essence, it's a templated automated validation software. So you build out test templates, you put in all the steps of how you want to check everything, and then you go in and assign the tags and the values. And we've built it in a way that it actually will export out a test procedure document. Not only will it give you that documentation, but it'll automatically execute that procedure for you. It's not running a script. It's not like coding behind the scenes that you're running some complex script to run through a test. You're actually building a test procedure document and hooking it into the tags and the addresses within the system. That's done almost automatically with our software so that it can step-by-step run through a procedure and confirm pass, fail on each of the expected results.
So what's interesting to me about that is sometimes when you adopt a technology you have sort of committed yourself to that technology to where there isn't really a manual option. But what I hear is there in the traditional workflow, there is a creation of a procedure that is a tedious manual creation. What we're saying with Test Drive is we have an efficient way to create that procedure by using templates, and so you create a procedure in less time than you would if you just did the traditional way. Then that procedure is automated, so it runs a full check. So it's like a digitized procedure check combo. And then even if you wanted to, you can still take that piece of paper and you can go do a manual test if you had to. So even if you had some change in philosophy or some technology adjustment or something, you still have the option, the manual option. So it's like you're not committing to a technology that is undermining anything that you've done in the past. It's really building upon that and saying, in the best case scenario, you've got a smart procedure with an automated test.
Absolutely. And we live in a world, it's not all black and white. And there, in some cases, there's things you can automate and there's things you can't. Well, in a test procedure, a lot of times you want a hybrid of that. Maybe there's some manual steps that you need to validate from the field even. That may be an option. There's things on external systems like a DCS, HMI that you may or may not be communicating with, or even if you are, you need to verify like coloring and animations on a graphic. So we wanted to build a system that was flexible enough to handle our workflow. So automate what can be automated, but also allow for manual step execution and validation. So we built a package that will do all of those things.
Okay. And then the one that is going to get everybody's attention is then cost savings, right? So we've got a more thorough test. It's repeatable. And it's fully documented. So when you're done, you get this full printout of everything that happened. How does that add up to cost savings?
Two ways. One is the cost versus a traditional method of producing those test procedure documents. Based on feedback we've had from our clients, it's upwards of 80% cost reduction just on the development of the test procedure documents themselves. Okay. Right. So you can save a lot of money even on an engineering project implementing this early on. What we were surprised with when we took Test Drive to market was our clients told us, that's wonderful. You'll save me time and money on my projects, but you'll save me a fortune if you can reduce my downtime during testing during an outage. So now probably 90% of our Test Drive work is focused on existing commissioned systems where we're coming in and automating the test. We're doing a much more thorough test than what's typically done, and we're doing it in anywhere between 4 and 10 times faster than what is traditionally done with a function test or a proof test. So what's that add up to? That adds up direct savings from what would have been lost production. We're reducing the downtime. So cutting, in some cases, multiple days off of a turnaround schedule by reducing the critical path.
Okay. So you've got savings in that there are less people needed to run these tests. There is less time required. And then that adds up to not only the manpower savings, but adds up to the savings of a critical path where you have a business, a facility that is down for a maintenance event, a turnaround as you called it, which is a time for improvements and maintenance. And so in being that critical path, that the last thing that has to get checked before you can restart the facility, we're really seeing that being one of the big value drivers there is shortening that time and allowing the facility to get back up and running. Is that right?
Absolutely, yeah.
Okay.
We always recommend you implement Test Drive as early as possible, like with an initial project where you're putting it together. But the fact of the matter is, thousands of these systems are out there or more, and they're in operation and they have to be tested, they have to be maintained. So we'll do all of them, right? We'll do the engineering projects, we'll do the existing commission systems, whatever it's needed. We're trying to help folks have more confidence in their safety systems, find the errors before they actually there's a demand and it doesn't do what it's supposed to do. So improving the safety and the quality and documentation, but really from a cost perspective, that really helps sell it internally, is being able to show just immediate ROI on the investment by reducing downtime.
Okay, and so we've stated a couple of benefits: less time, less people. Another benefit is compliance. So how does this improve compliance with the overall standards?
Well, auditability, right? Being able to prove exactly what you tested and what the system response was. We have a recommended set of documentation that we give our clients. Here's what you need to store along with every system. So you need a copy of the configuration at the time you tested it, a copy of those design documents that outline the way it's supposed to function, and the test results themselves. With that's fully repeatable. You could run that same test. You run a test drive test on that same configuration and get exactly the same results. But that's auditable. You can prove that you ran all of these tests, and you can prove what your system did.
Okay. One other point I think is, in the industry, we've mentioned some vendors here, but the test drive solution is agnostic or independent of vendors. Is that correct?
Yes, so we write our own communication drivers that communicate directly with the platforms, and this could be anywhere from an emulator or simulator, if they're available, depends on the vendor, or the physical hardware. But it's important to note that all test drive tests are non-destructive. So we communicate directly with the platform for purposes of simulation and testing to make sure it does what it's supposed to do. But you do not have to modify your configuration in any way to enable the testing.
Okay, excellent. So platform independent, which allows you as an organization, typically these plants are not only one type of vendor, right? So you've got a facility and it's going to have some Allen Bradley, might have some Triconics, might have some Honeywell spread across the plant. And so when you've got a system that can communicate with all three of those and run the exact same style of test, then you're also building a work practice for people where they can have consistency. Because in the industry, these vendors typically have their own solutions for a lot of items, or they have different circumstances because they're built differently. Is that right?
That's right. And we really wanted to be a vendor agnostic solution. And even ourselves, we didn't want to bake us into the workflow to where we had to be there all the time. So we deliver test drive to our clients, and they continue to maintain the configurations and run tests without us involved at all. And we deal frequently with sites or companies that have a wide variety of different platforms: Triconics, Delta V, Honeywell System, Safety Manager, you name it. So we want to enable testing on all those platforms, but give you a common front end so that makes your workflow easier. Too often we were dealing with just the pain and the difficulty of developing test procedures, maintaining them, executing them. We wanted to simplify all that, one, to reduce cost and help our clients make more money, but ultimately to make safer facilities that protect people and protect the equipment.
Right. Yeah. I mean, there's no denying you could see the faults in the older methodologies. I mean, there's definitely room for improvement here. And this allows a programmatic approach to that. Sounds really, really good. Last thing, any quoted numbers from particular projects where you can kind of give an idea to the audience of what the value might have been?
Yeah, we had a series of projects with quoted savings over $2 million. One of the first jobs that we did for one of our major test drive clients, they confirmed over $500,000 of savings just on the initial project. And you're talking about a test drive implementation. It varies obviously with the size of the system, but maybe $50,000 being able to immediately save you $500,000 up to $2 million in lost downtime. Not to mention the manpower savings and the schedule savings on engineering projects as well. So in most cases, what we see when we actually receive feedback from our clients is an immediate ROI on the implementation of a test drive system.
Okay, awesome. Well, I appreciate you sharing that and breaking that down with me. We as a company, This is a niche area in automated testing. It's one that's gaining some momentum, and for anybody out there that's listening and wants to know more about it or whatever, just look us up on the website and send us a note, and we'd be happy to share more information. So thank you, David, for coming in.
Thank you, Mike.